Morning, everyone. How's it going? Actually, let me refill my water real quick and then we'll get started. All right. Any questions before we get started today? All right. Let's see. On Friday we started chapter 5. We began talking about work and energy. We're going to continue that today by looking at different forms of energy, how we transfer between them, talk about the law of conservation of energy, and my goal is to wrap up chapter 5 around Wednesday so that we can spend Friday summarizing everything before test week next week. As a reminder, I will have study materials up this week for you to be able to use for that, and we will spend class time talking about it and going over it. For right now, we began talking about energy, and we have defined energy as something invisible that matter is able to possess that allows it to do stuff. And that is an apt description for all forms of energy, but there are multiple different forms, like there are different types of force. And so we need to start looking at the different forms and how we talk about how we calculate the different forms. This class is mostly mechanical in nature, and so the forms of energy we talk about in here are going to be mostly mechanical in nature. That is to say, having to do with motion and matter. Non-mechanical forms of energy, like light and heat, for example, aren't considered mechanical because they aren't causing things to move. We're going to stick with mechanical. And easily the most directly noticeable form of mechanical energy is just kinetic energy. Kinetic is just the term for motion, or of or referring to motion. So kinetic energy is just movement energy. If you can see matter moving, it has kinetic energy from your frame of reference. So the formula is just Ke equals 1/2 mv squared. Each individual form of energy is likely just going to have its own acronym. And I keep them all capitalized to make it clear that none of these are subscripts. It's just the one thing, Ke. And an object possesses kinetic energy if it has mass and is currently in motion. So if you're not moving, you don't have kinetic energy. And if you don't have mass, you can't have kinetic energy, even if you are moving at the speed of light. So light does not have kinetic energy specifically. It has something else. Energy itself, all forms, is a scalar. So Ke is not a vector. This will never have a direction attached to it. Although, interestingly, we do use a vector to calculate it, but because the velocity term is squared, the direction attached to it just kind of vanishes. Ke doesn't care what direction you're moving in, it just cares that you're moving. If you are energized, you just gotta go. And the universe largely doesn't care in what direction you go in. I will also point out that because the V term is squared, it matters more than the M term does. If we were to double the M term in this formula, you'd get twice the Ke. an object with twice as much matter would require twice the kinetic energy to go at the same speed. But if you take two objects of the same mass and double one of their velocities, you would quadruple its energy requirement. So 2 squared would be 4 instead of 2. So what this means is the faster something goes, the exponentially more energy is needed to get it to go at that speed and to keep it at that speed. Going fast takes exponentially more energy. And you've probably noticed this when running. Running just tires you out faster than walking because of the energy requirement. If you walk across campus, you will burn more energy, you'll burn less energy than running the same distance. You'll just get there faster. In an interesting way, this also contributes to why we don't have interplanetary travel yet, because to get anywhere in space, you gotta be moving pretty quick. It'll take years to get to Mars, moving at any speed, really. And so if you wanted to go like warp speed in movies and stuff, you would need to be moving the speed of light squared times the mass of your ship, and that'd be the energy requirement. We don't have that much energy. We're not going that fast. And if you did, you might tear open a black hole, if I'm being honest with you. So, going fast takes energy. It's true for spaceships, it's true for humans. It's also true for your car. You burn more gas more quickly if you're going at a higher speed within the same gear. So the most efficient thing you can do is go at the lowest speed in the highest gear. Lowest speed, highest gear, which may only make sense if you drive a manual. Questions so far? All right. So, it's not a long formula. We'll just get a quick sample for it. Here we have two different entities with two different masses and two different speeds. Which scenario features more kinetic energy in it?
Case B.
Case B, that is correct. I said that the V term is squared, so it's more important, but that does not mean that the M term is to be ignored. Are we going to plug 5,000 into our formula?
No.
No, what will we plug in?
5.
Very good, 5 kilograms, velocity squared. When putting stuff like this into your calculator, make sure you are only squaring the velocity term. So this would be the same as 1/2 times 5 times 9, and that should give us 22.5 joules. Meanwhile, the person walking is at a much lower speed, but has a much bigger mass. And so they have 50 joules of kinetic energy. So depending on the mass of your body, walking is more strenuous than throwing a bowling ball. Doubly so when you factor in that friction is constantly trying to leach that kinetic energy away, and you have to do more work to regenerate it. So, the V term is important, but the M term is not to be ignored. If we did, you know what? Just for argument's sake, so as I said a second ago, sci-fi likes to go to warp speed a lot, because in order to get to another solar system, you have to be moving faster than light to get there in a reasonable amount of time. It would take 8 minutes going at light speed just to get to our own sun, let alone another solar system. But let's just look at the energy requirement to get a person up to light speed. So this is the speed of light, 3 times 10 to the 8th meters per second. We're going to take that times 10 to the 8th and square it. So this number has at least 16 zeros for its energy requirement. I don't know if we have that much energy on the planet. going light speed anytime soon. We have to figure out some hack for it. We're not accelerating there the old-fashioned way. All right, that's just one form of energy. There are several, as we've hinted at before. So let's talk about a slightly weirder type. Raise your hand if you've heard of this one before. Okay, not zero people. Gravitational potential energy. If you haven't heard of GPE, are you at least familiar? You're at least familiar with the concept of potential energy, energy in potential. For example, chemical potential energy in food and inside your body, and in chemical batteries as well, actually. So this is a stored form of energy, but rather than stored in a potential reaction, it's stored in an object's ability to fall. It is stored in something's height above the ground. I promise I'll make sure that makes sense. The formula for GPE is mass times, that's the same lowercase g that means negative 9.8, by the way. M times G times H. H is height. Height from your frame of reference. I'll also point out, since all forms of energy are scalars, this formula doesn't actually care about the negative sign that lives on G, and we actually want to put absolute value brackets on there to cancel it out. Negative GPE implies losing GPE, not downward GPE. Again, you don't have downward pointing energy. Energy doesn't point anywhere. So this formula does not care about that negative. I would add absolute value brackets to your formula sheet if they are not already there. They are not. When an object is able to fall, there is energy stored inside of it, and that energy is released once it begins falling. If I hold this eraser in the air, it could fall, and when it does fall, it has a velocity. In that moment where it starts accelerating and gains velocity, it must now have kinetic energy where it didn't before. And that kinetic energy was created when the gravitational potential stored inside of the eraser is released. So the energy's there, it's just not doing anything until the object starts falling or descending in some way. And it may be weird to think of as energy stored in the ability to fall, so I'm going to offer an alternative explanation. GPE can be thought of as the energy required to get an object to that height in the first place. Energy that you store in the item when you elevate it to that point. Because on Friday we talked about work, correct? So this formula looks familiar by now. Work equals force times displacement. And that means when you lift something, exerting a vertical force on it, lifting it upwards some distance, you're doing work on it, correct? And interestingly, when you lift something upwards, you have to at least exert as much force as the weight of that object. So instead of force, I'm going to write M times G. That's supposed to be G. Because the force we're exerting is equal or greater than the weight of the object. And the distance I lifted is equal to the change in height of that object. So secretly, the GPE formula is just a hyper-specific version of the work formula, because the GPE something has is equal to the work that was needed to be done to get it there. So when I lift this object, I'm burning chemical potential in my arm and turning it into GPE in the eraser that is released when it falls. It has that stored energy. It must, because it can then turn into KE. So, two definitions: energy stored in the ability to fall, energy stored within your location within a gravitational field, but can alternatively be thought of as the work required to get it there that is currently still stored in the object after the fact. Now, height is kind of a relative term, excuse me. So what exactly an object height is kind of depends on your frame of reference, because right now we could say me standing on the ground, I have no gravitational potential energy because I'm standing on height of 0, correct? We could say that. But just because my feet are on the ground doesn't mean my center of mass can't fall, like my torso can fall to the ground. And likewise, I could fall really far if there was just a hole under me. I could fall all the way to Earth's core if we had a hole deep enough. So again, height is kind of relative. This is one of the most relative forms of energy we'll ever talk about. So for any given question, it's important to decide where your 0 height is, where your 0 level is. And as long as all your answers are in reference to whatever you set h equals 0 as, I'll count your work as correct. I'll try to give you a height of 0 to work from so you don't have to make it up on your own. Questions about the concept so far? All right. One more quick sample calculation. Which of these two scenarios has more GPE? 5,000 grams again, 10 meters up, versus 100 kilograms, 10 centimeters up.
Object A.
Object A, how much does A have?
490.
Very good. How much does B have?
98.
That's correct, because we have to not only convert grams into kilograms, we also have to convert centimeters into meters. So, main thing for right now is just continue checking your units. All right. That is two distinct forms of energy. And so now we need to talk about how one gets turned into the other. Law of conservation of energy is one of the physics principles that makes it into common parlance often enough. Energy cannot be created nor destroyed. It simply transfers between states and between different objects. This is true for systems, which is to say, whatever number of objects you're currently studying. But it's also true of the universe as a whole. There's a certain fixed amount of energy in the entire universe. The total doesn't change, even if that lump sum of energy will constantly be alternating between forms and between which single object currently possesses it. For the sake of our math in this class, that's going to mean that the total initial energy in whatever system you're examining, total of every single form that object can possess added together, is going to equal the final total of all of the forms that object can possess added together. Whenever some sort of a change takes place, any change, any motion, any process that can do work, that can take energy and turn it into another form or send it somewhere else, The totals remain the same across the both sides, even if the forms are not the same on both sides, or the object distribution is not the same on both sides, but the totals add up. And we are going to begin applying this and examining the energy flow in certain situations, from start to finish. This is going to kind of introduce us to a new genre of problems where we have a scenario where something happens and we need to compare the initial condition to the final state after the process has completed. So that's why there's an initial side and a final side. Questions so far? All right. Well, let's examine a process where energy will change states from start to finish. This type of scenario should look familiar. We're going to take a bowling ball and throw it straight upwards. And we've done questions like this using the first couple formulas that we learned about, but we're going to do it now through the lens of energy. Here we have our bowling ball, and I'm suddenly realizing that bowling balls are just large plastic coconuts. Mass of 10 kilograms, we're going to launch it 4.5 meters. We're going to launch it at a speed of 4.5 meters. And for simplicity's sake, we're going to assume this thing starts at the ground at a height of 0. And we're going to analyze its energy levels in various types as it rises. So, what form or forms of energy does the bowling ball possess at the beginning, right as it's launched? Kinetic. It has a velocity, it's in motion, therefore it must have some amount of kinetic energy for that to be true. So, kinetic energy initial, I'm going to do 1/2 times mass times initial velocity squared. For the ball to be moving at that speed, it would need 101.25 joules of kinetic energy for that mass to be moving at that speed. Something had to do work to give it that amount, but we're considering our initial state here. That has already happened. We've launched, we've started our stopwatch right there at launch. It already has the kinetic energy, and now it's going to do something with it. Before I actually move on to the next question that's written, how much GPE would the bowling ball have at this initial state if we consider our starting height to be 0?
At the starting height is 0, GPE is 0.
Yeah. If you consider your initial point to be height of 0, then you will not have any GPE within that frame of reference. So just to go ahead and get that written down, it'll come in handy later. Initial GPE will be 0. Our initial KE is about 101 joules. So, we got a lot of KE, but no GPE at the start. And what's going to happen to those two energy levels as this thing ascends?
The GPE will rise as it goes up.
Because as height increases, you won't plug 0 in anymore. You'll get a bigger and bigger GPE as you go up.
And once it reaches its apex is when it will reach its max GPE.
All right, at the maximum height, it'll have the maximum amount of GPE. So GPE is going to increase from 0 to something as it elevates. What's going to happen to its KE as that happens?
Kinetic will decrease. decrease as velocity decreases.
Right, because this is a projectile. We know from prior examples it's going to be accelerating down the entire time. What happens to its vertical velocity while that happens?
Decreases to 0.
Decreases to 0. So at that maximum height, whatever this is, its final velocity at that point final vertical velocity should be 0. And so, KE will drop on the way up as the speed drops. And every single joule of KE that it loses, it will gain as GPE. If we say pause the process partway through here, like literally halfway up, it'll have lost half of its KE and gained that amount of GPE. Yes?
So with that being said, every joule that it loses as kinetic energy will transform into GPE. Does that mean GPE at the apex will be initial kinetic energy?
Yes. Good observation. And I'm going to demonstrate that now using the conservation of energy equation. All of these initial forms are going to add up together to tell us the total initial energy of the bowling ball. And that total initial energy level will be the same as the total final energy level, even if it's distributed differently. On the initial side, we've got a lot of initial KE and no initial GPE, but I'm going to list it here for completeness sake. And those levels are going to change to a different amount of KE and a different amount of GPE at the end. So here I've got final values on this side. And note again, total energy initial, this is all of the initial energy forms added up together, equal on the other side to all of the final energy forms added up together. And the totals on the two sides will remain the same, even if the forms change from one side to the other. Now, we've already got values for KE initial and GPE initial, excuse me. So I'll plug those in. And on the right side, exactly what these are kind of depend on which point in the process you're examining. I'm just going to plug in the generalized formulas for now. What this tells us is, at any given height, at any given point this thing has risen to, it'll have a certain amount of GPE, and there'll be a certain amount of KE left remaining, depending on whatever height we happen to choose. If we chose a height about halfway up, whatever value for H we plug in here, we could solve for however fast it's moving in that moment. So this is meant to show, depending on the relationship between the final velocity and the final height, you can have a different mix of the two forms depending on which spot you're examining, because partway up, you do possess both types at once, but their total will still add up to the same total. The extreme case is at this final height here, where we know that VF is 0. And at that point, if VF is 0, that means we've got no kinetic energy left, and therefore, let's kind of cancel out all the zeros here. GPE initial is 0, and at that maximum height, VF is 0, which means that KEF is 0. And so for this process, all of the initial KE will turn into final GPE at that maximum final point. At that highest point, you've elevated as much as you can, and you've stopped for a second. And we're just going to pause time right there. Now again, we've described this using acceleration in the classic formulas before. We're just doing it through the lens of energy now. Any questions about this concept before we find a number for H? Okay. So, again, I'll show. everything for completeness sake. At maximum height, final velocity is 0, so this whole term is going to go away. And at that point, all of the energy will have turned into GPE. So if that's 0, then height final would be 101.25 over 98, which is 1.03 meters. So if you can take a 10 kilogram bowling ball and chuck it at 4.5 meters per second, you could get it 1 meter into the air. And then you'd want to move because it's coming back down. So that's the height where all of the energy has turned into the gravitational potential state. And if we then unfreeze time, what's going to happen next?
It's going to fall.
It's going to fall, and that GPE is going to turn right back into KE. How do you guys feel? All right. Yeah, as I just hinted at, this process can go in both directions. And to demonstrate that, I want to show a slightly different example that involves starting up here and then falling down, but I've changed the flavor text a little bit. Because strictly speaking, you don't have to be falling for GPE to transform into another state. It happens whenever you are descending. Because again, it depends on where you are. Like your current GPE level depends on where you are in Earth's gravitational field. It's not specifically in reference to the act of falling. So as long as your height is changing, your GPE level is changing. And therefore, that GPE, like if you're losing GPE, it could be turning into something else. And so in this case, we're gonna just show GPE turning into KE, sliding down a hill, rather than just falling back down. Any questions or issues before I erase the bowling ball? All right. So, that's a little better. We're going to have a skier up here, on top of a 30-meter tall slope. That's like a 10-story building, so this is not a beginner activity. Mass of 85 kilograms. And right there at the beginning, they aren't moving yet. They're just in position, primed, ready to go, and they're just going to let gravity do the work for them. So, first question, what form of energy do they possess at that starting height?
Well, is that they have GPE, but it's not going to be straight down.
They have GPE, and yeah, for right now, let's just calculate how much they have up here, because as long as you are elevated above some other point, you have GPE in comparison to that second point. So as long as we are 30 meters above something, we have GPE in relation to that lower spot. So GPE initial, and my M's look weird today. MGH initial, 85 times magnitude of 9.8 times height of 30 gives us a lot of GPE, about 25,000 joules. Again, 10-story building. And you are correct, this person is not going to fall straight down. But upon descending, in any way, shape, or form, that energy is still going to be released. And we're going to choose to release it in a way that's going to turn it straight into KE. Because if you're sliding down a slope, your GBE is still going to turn into KE even if you're not falling straight down. It's just not going to happen as quickly as if you were falling straight down. But you'll still get the KE, you'll still end up at a final speed, you just won't do it as fast. But as long as you are descending at all, falling or not, GPE drops and that energy has to go somewhere. And in this case, we're going to use a frictionless slope to try to turn it directly into KE. Also add, if this is your starting GPE, that means that you would have to do at least this much work to climb to this point. That's a lot of work. Take the ski lift. We're also going to assume that we aren't moving at the start. So no initial kinetic energy. We're just going to get off the ski lift and let gravity take over. Now, as you descend this slope, what's going to happen to your GPE level as your height decreases? Yeah, I probably said it already. GPE is going to go down. What form is it going to turn into?
Kinetic.
Kinetic, because you will acquire a velocity and it's going to get bigger and bigger all the way down. So descending tends to transform GPE into KE, even if it's a little more indirect. We're not falling straight down, but we are still going through a process to turn GPE into KE. So our initial forms of energy add up to some total on the initial side, and on the final side, they will add up to the same total. And if we wanted to, we could plug in any final height to try to figure out your speed partway down, figure out how much energy has transformed at which points. But we could also plug in a final height of 0 to figure out how fast you're going at the bottom. The point where all of that initial GPE has turned into KE and you were moving as fast as you can go. So, KE initial is 0. We've also determined that GPEF will be 0 at that lowest point, demonstrating again, all of that initial GPE is going to turn into KE at that point where you're moving at your absolute fastest. And that's going to look like 24990 equals 42.5 times VF squared. VF is then going to be the square root of 24990 over 42.5, which, if memory serves, is, please correct me if I'm wrong, 24.25 meters per second. For a sense of scale, that is meters per second. That is over 24 meters every second, which translates to over 80 feet every second. This person is booking it. This is a black diamond slope. Buyer beware. I don't know. Be careful. Now, realistically, friction would interfere with this because snow does not eliminate friction, it just reduces it. So in real life, you'd be going slower than this. How much slower depends on how good the snow is. But you would be going slower. That said, this is still fast. And you'd get the same speed if you tried to figure out how fast this person would be falling if they just fell straight down from a 30-meter height as well. What the slope has done is it's just kind of gradually taken what would be vertical speed and gradually tilted it sideways. So slopes have the potential to turn your straight down final velocity into a horizontal one. And if you eliminate friction as much as possible, it can be pretty close, as close to 1-to-1 as you can get. Realistically, it'd be less, but it's better than, you want to be going sideways. You do not want that speed going straight down. I think I'm rambling at this point. How do you guys feel? All right, so energy transforms between types. The total amount is always constant, even if the types aren't constant. This gets more complicated when friction is involved, so we'll cover examples where that is the case. But we are also going to cover examples that involve other types of energy, because there is a lot of types of energy. So the last thing we're going to do today is at least introduce the next type, since lab this week involves it. So this is a third type. It is another form of mechanical energy, so it still has to do with motion or the potential for motion. This is called elastic potential energy. The potential meaning it is still a stored form of energy like GPE, but rather than being stored in falling or stored in, say, chemical bonds, this is stored within stretch. This is stored in an object's current deformation and ability to return to its normal shape. To give you a few more vocab words real quick, an object is considered to be elastic if it can deform and then return to normal all by itself. Loads of objects are able to deform. For another vocab word, deformation just means you change its shape somehow. Loads of objects can deform. You can hit anything with a hammer and deform it. But it's only elastic if it then goes back to normal by itself. Hit a rock with a hammer, it's going to break and it will not fix itself. But if I stretch this spring, it can go back to its original length without me interfering. I'm not going to do that because I'll pop my knuckles. But it can. It has the ability to. And for that reason, it is elastic. And when you deform it, you actually store energy in that temporary deformation. It's kind of hard to see with your, in real-time human eyes. But when you dribble a basketball, as it hits the floor, its velocity temporarily drops to 0 for a split second, because on impact it's going to stop moving for a moment. But in that same split second, it's no longer spherically shaped. For a split second, it pancakes. Which means, physics definition, it has deformed by some distance. So in that moment, velocity drops to 0 and it pancakes. It then blorps back to normal and ricochets off the floor, correct? That happens because as it approaches the floor, it has kinetic energy. When it hits the floor and stops for a second, its KE drops to 0. That energy has to go somewhere because it can't be destroyed. And ideally, all of that energy is now stored in the deformation of the ball. Because whenever you stretch something, either outward or inward, it takes energy to do that, and energy is then stored inside of it. This is why whenever you whip a rubber band, it moves afterwards. I store energy in it, and then it releases into probably the kinetic state. And that's what allows the rubber band to move, and it's also what allows you to launch things. using elastic objects. I'm not actually going to do it. So, slingshots, or even just launching the rubber band at your younger brother, I speak from experience. Energy is stored. I'm doing work and storing energy in it that is then released when it goes back to normal. So when the ball unpancakes, the energy that's stored in it releases back into the kinetic state, and that's why it's able to bounce back up off the floor. As opposed to, say, if you watch Looney Tunes, an anvil, which just makes a crater. Because it doesn't squash and stretch, it just hits the floor and all the energy just imparts into the floor and breaks it. Whereas here, the energy is temporarily stored inside the ball and then released, allowing it to spring back up. All elastic objects do this, usually made out of rubber, but also springs, as we're going to find out in lab this week. And the amount of energy that's stored inside of something, EPE, elastic potential energy, is equal to 1/2 times the object's spring constant times x squared. X is the magnitude of deformation, the current change in length of the item. In the case of this, it would be like if the ball is normally like 10 centimeters in diameter and it pancakes to 5 centimeters in diameter, the delta, the x, would be the 5 centimeters it lost. It changed size by 5 centimeters. It is very specifically the change in size. It's not the final size. Say this spring is normally 1 meter long and I stretch it to 2 meters long. What is the magnitude of deformation? It was 1 meter, now it's 2. 1 meter, exactly. It got 1 meter longer, even though its current length is 2. This number is meant to be the change. I suppose it should be delta x then, sorry. It's the change in length, not the final length. Change in length. Does the formula have delta? Does the sheet have delta? It does. Fantastic. Your formula sheet is correct and my notes aren't. So the delta x term is change in length. The k term is a new constant called literally spring constant. And this tells you how stiff the spring is, basically. Higher spring constant means that item takes more force to physically stretch. And likewise, a lower spring constant means it takes less force to stretch. So this particular spring has a pretty low spring constant because I'm able to do this pretty easily. And the bigger the spring constant, the more energy you can store in the stretch of that item. Every different elastic object has its own spring constant, so kind of like how I will never give you a table of mu's to memorize. You don't have to memorize K. I'll either tell you what the spring constant of something is or give you the tools to find it. Most often you can find it with this formula, because not only does spring constant tell you how much energy something can store when stretched, it can also tell you how much force is required to stretch it. Force stretch is equal to spring constant times deformation. If this thing has a spring constant of 10 newtons per meter, it would take 10 newtons of force to make it 1 meter longer. And then 5 newtons per meter would be 5 newtons to make it 1 meter longer. So, and this is one of the things we're going to be practicing in lab this week and also on Wednesday. How do you guys feel for right now, for our third energy type? All right. Bring these notes to lab whenever you have it. Lab will involve all 3 types. I'll devise a machine that will have all 3 forms in it at once. And let me know if you need anything. Happy Monday. Have a nice day. I'm rambling. Go have lunch.